Get a little red symbol. Alright, so I want to get to Blackboard, and as we all know, it's not behaving, so I have two other tricks up my sleeve. First, I will stubbornly try to get on it one more time. This way. I tried going through Safari, which sometimes works. So it's Blackboard, ttu.edu, hit the return, go to login, and it goes into sleep mode. Well, while that's deciding to work, let's go ahead and start the lesson, and if it comes to life, we will proceed back to it. Okay, that's a good sign. So today's lesson is lesson 19, which is the one that comes just before 20 and just after 18. And then when we get to lesson 21, that's a very happy birthday for the lessons, right? And there we go. So the title of today's lesson is Prediction Engines by Regression. That's a pretty fancy title for something that we've done as scientists and engineers for several hundred years. But put the word prediction engine, that makes it modern. And regression is a type of machine learning because the machine is doing the work. And so now we're all completely up to date and modern. What we'll do today, both in lesson and in lab, so the lab is very much like the lesson. It does not have identical examples, but for all practical purposes, they're the same. We'll make some linear regression models, first using primitive Python. The main thing you'll get out of that is that that's an obnoxiously intricate way to do something that's real simple if you install the correct package. Then we'll do it with the correct package. And from that point forward, there is no good reason to do it in primitive Python unless you just can't get anything else to work. So we will start with a little bit of background on linear regression and what it does. So regression itself is a fairly fundamental and commonly used type of predictive analysis. And the overall idea of the method, we've actually seen it in kind of a roundabout way. Let me see if I can get my electronic drawing thing up and running. So you remember graphs. Oh, that's not a very good graph. What's missing? Everything. More precise than everything. All right. Label. Okay, what label do you want me to put on the left-right axis? Keep it short, like maybe one letter of the alphabet, please. Thank you. Up-down axis? Why not? That's why. And then we had stuff like this, and I think I use blue dots and red lines, or red dots and blue lines. It doesn't really matter. We had dots and lines. The dots represent observations, and then we try to put our model through the dots. Now that one I just drew intentionally was not the greatest one in the world. Let me see if I can do this for the people out there in TV land. Okay, TV land. There's what I just drew. Bet you can't actually see it, but it is getting caught on the recording. So we will shrinkify that. And to this point, we looked at simply by trial and error changing parameters of the function that makes the blue line, trying to make it go through the red dots. And we did have one way of measuring how close the blue line was to the red dots. Anyone remember what that was? It began with the letter R. Yeah, we would measure the collection of these distances. Generally, we would square those distances so that the positive and negative distances don't cancel each other out and give us the illusion that we have a great model, which when plotted is otherwise absolutely absurd. So we can extend this idea mentally. Imagine that the blue line is connected to the red dots, which are fixed in space, with little springs, or big springs, whatever. That's just down the road a bit. Okay, so we have these springs there. And remember from physics, the energy stored in a spring is equal to the spring, at least a linear spring, is a spring constant K times how far deformed it is from its resting state. So we're going to pretend that these springs are real, a resting state really teeny. So we've just strung this blue line that's rigid in there, attached it to the red dots with strings. In the current drawing, we see that this spring, and that spring are pretty well stretched out. So when we let go of the blue thing, it's going to flop around. Those springs are going to get shorter as they try to reduce their energy. And these ones that are already short, they're going to get longer because they're going to take on that energy. And at some point, we'll get an equilibrium condition, which is the minimum energy for that system, minimum spring energy. And so if we do that, I'm just going to try to eyeball draw this. That's what I always do, right? That's supposed to be a straight line. Ignore the curvature that's working its way in. So at this point, we will declare that our minimum energy solution. It probably doesn't look exactly like that, how I've drawn it.
What's the new blue line you drew?
That's the one where I let go of it and all the springs came to equilibrium. And now they're holding the blue line at the lowest energy that will fit between the points. That is a mental physical model of something called least squares minimization, where the sum of the distances represents the stored spring energy. Okay, so that's a fundamental mechanical idea of what's going on in regression. And in this case, we used a straight line, but it can be curves, it can be logarithmic, it can be any function that we can dream up of. So the common ideas in regression are, one, does a set of predictor variables, modern word is features, do a good job in predicting an outcome or a response variable? So in this drawing here, let's say the fat blue line is our data model and the red dots are our red dots. Does that fat blue line do a good job of allowing us to predict y based on x? And most of you shaking your head, yeah, it does. I mean, there's obviously correlation because I drew the dots. So x is a good explanatory variable for y. Now, it could be that there is no correlation, there's no causality in it. It could be x and y are completely unrelated things. But that plot does have correlation, whether or not it has causality. The second thing we use regression for is to determine which of multiple explanatory variables are significant, in a statistics sense, predictors of the outcome variable, and in what way do they indicated by magnitude and sign of the beta estimates, impact the outcome. A third question is, what is the estimated value of the response under various variable values? And that's what we'll focus on mostly today. We want to get this blue line and then use it to predict or forecast values of y for given values of x that aren't necessarily in our observation collection. If the red dots all fell along in a nice line, that would be really easy because we'd only need to look at 2 points. And the last thing that regression does is it gives us some way of quantifying the uncertainty involved in the prediction. We'll get to that next class meeting, not today. So these regression estimates are used to explain the relationship between one dependent variable, the up-down, the y, and one or more independent variables. Here we can only plot x, but we could have at least 24 more letters of the alphabet without having to go to upper and lowercase, subscripting, and so forth. The simplest form is linear regression, which we have played with extensively throughout this semester, and we'll do some more, and one dependent or response variable. And it's defined by the formula that I have up here as y some observation is beta 0 plus beta 1x. Earlier we did it as intercept plus slope. We might have used b0 and b1 in some prior examples. The names of the parameters beta are irrelevant. They simply represent unknown values that once we state what those values are, it gives us a tool to predict y given any value of x. So what's it used for? Why does anyone care? Anyone here want to speculate an answer? Well, it's used for because that's what today's class is, and I care because I want this semester to end so I can move on with my life. Yes, that was caught on the recorder. Well, look at all those grins. There's those smiles. Had to wait 3 months for that. I guess I should have just led with that, right? So the 3 major uses for regression are determining the strength, that's a poor word, the value of the predictors, forecasting effect, and forecasting trends. And you can read faster than I can read it to you. But in identifying the strength, the kinds of questions we ask with that particular interpretation is, does X give us very much useful information about Y? If it's a weak relationship, a lousy correlation, a correlation coefficient approaching what number of the alphabet? 0. At least it wasn't a letter of the number bet. That is one way of using regression. And we can determine that based on the computed slope and intercept. Pretty much if that slope gets close to 0, because remember the slope in the linear model is directly proportional to the correlation between x and y. As the slope gets 0, there's no correlation. Your best guess of y is its mean value, regardless of x. Secondly, we can use it to forecast effects or impact of changes. That's fairly obvious. You put a value of x in, you read the blue line, what the y will be, and we can actually ask that either directly as a point estimate, or the way it's suggested here from business school is how much additional y do I get for an additional increment of x? That's basically taking the derivative, although they call it marginals because they're business people. That's why they make more money than we do, because they have better language to work with. But it's the same arithmetic. And then third, regression analysis can be used to predict trends in future values, at least to some extent, if x happens to be something about time. This last example might be, what's the price of gold in 6 months? That is kind of a stretch for a regression analysis, because that does imply causality, and our variable x would have to either have autoregressive characteristics or some other way that's a direct relationship between the question and what's driving it. So putting that aside, our engineering tasks are usually, what do I turn the dial to make the missile go to where I want, or something to that effect. Regression analysis and linear models and polynomial models and some other fairly straightforward ones work pretty well in engineering. Or at least they have for the last few hundred years. We're all still here. We haven't crashed the planet into the sun yet, although give it some time. We probably could achieve that. So let's look back in the 1970s. That was when P. pterodactyls roamed the skies. In 1977, I was in the Federal Republic of Germany, which was to the west of the German Democratic Republic. The German Democratic Republic was not democratic, but that's how communist countries named themselves back in the 70s. So this is definitely olden days. So let's read this. This comes from a calculator instruction manual. In many disciplines, it's desirable to express one variable in terms of another, even though the variables appear independent and are not necessarily analytical functions of one another. So that was the correlation causality thing, translated into something that people could read who were buying these calculators. An accepted practice is to perform least squares linear regression, which is designed to minimize the sum of the squares of the deviations, make our springs collectively as short as possible, so that their kx term, which represents the energy stored in the spring, is a minimum energy solution of the actual data points from the straight line of best fit. In practice, we're essentially constructing a plot of the variables called a scatter diagram. So that's not a new word. They even use the word scatter in Python. Go figure. And drawing the best straight line which uniformly divides the data points as shown below. Because real data may not actually be on a straight line, it's desirable to measure how well the curve fits the data. And this measure is called the correlation coefficient and may be calculated from the independent variables and linear equation parameters. Or we could just use the correlation function in our program to do the same thing. In the context of this class, the straight line shown here in the diagram that I'm moving the cursor up and down. Oh good, you're all starting to look nauseous, so the cursor's working. That is our data model. It is a model of the dots. And that's not a bad model because at least the dots and the lines appear in the same graphic. And perhaps you all have personally experienced in this class where the dots and the lines are so far apart you can't tell where either one is. If not, you will. And if not this class, some other class. So that's our data model. And the function of the equation for the data model is y equals beta 0 plus beta 1 x. And I've done those capitalized and bold faces to remind ourselves that they could be matrices and not just single-valued variables. The ordered pairs xi, yi in the scatter plot are actual observations, or in the jargon of machine learning, the training set. As depicted here, cap y is the response to different values of cap x. The typical convention is that response is on the up-down scale, and the explanatory variable is on the left-right scale. That's not always the case, but that's pretty common. And if you're a person that needs to have rules of thumb to get through life, that's a good one. That'll serve you mostly well unless you take civil engineering classes, where one of our variables of interest is usually depth. And because we think funny, we plot depth on the up-down, and we're using depth to predict things. So civil engineers are certainly different in that respect, and probably the other disciplines are in their own way too. So the model parameters, the unknown values are beta 0 and beta 1. Once we know what they are, we can predict the response, the cap y, to any input cap x. Classically, these betas are recovered from something called the normal equations, not to be confused with the Abbe-normal equations. And if you can't guess what movie that's from, let me cover up the microphone so the people who aren't here won't know that it was Young Frankenstein. And they're shown here. You'll notice that you have some x's and some y. If you look at those carefully, you have a covariance component, a variance component, that's the sum of x squared. Things are divided by n. And then you have the mean values of the two series, which are used to give us information about beta 0. Essentially, beta 0 is the mean value of y minus the correlation coefficient times the mean value of x. That's what those equations are telling us. So let's look at, I actually have the actual data from the user manual circa 1977. And so we will use that and we'll illustrate regression by the classical normal equation approach. I'm going to go through it quickly. There's a lot of scripting here that nowadays is somewhat superfluous. Oh, that almost came out right. And you probably wouldn't want to do it this way, but we'll see it done once in primitive Python, then we'll see it done with a couple packages. And what we gain out of the packages is much more compact scripting for us, the human beings, to manage. What's going on underneath the hood is the same. We'll get the same numbers out. So in doing this example, let's first make a plotting package. And the name of this plotting package today is, we went to the mall and we went to the Build-A-Bear shop and we bought the Make-A-Bear package. So Make-A-Bear takes a list of x values and y values, and that will be rendered as a scatter plot. It takes an xy point on the left side, an xy point on the right side. It's going to draw that as a straight line, and then some information on labels and titles. And we have this nice comment block that tells us what each piece is. There's another way to do that block. It's with the triple quotes. It does the same thing. And this one will get our matplot library. It'll plot the scatters as default color. It'll plot the straight line as dash line. And then it renders the plot and does the show. So now let's make the two lists. So the data we're going to examine are the sample length of a fiber that's for fiber reinforced polymer and the associated sample weight. The lengths are expressed in centimeters and the weight in grams. So if we have 101 centimeters, that's roughly a meter. 3 1/4 feet, and it weighs 600 grams, 6/10 of a kilogram. So 6/10 of a kilogram is 1.8 pounds. It's actually kind of heavy for a 1 meter piece of polymer, but you see it has the word NASA on it, so we already know that that makes it heavy and expensive. That's why spaceflight's not cheap yet. Okay, so we have these observations, and so the sample length is all around 1 meter, and the weights are roughly around 600 grams. So let's go ahead and run the script. Oh, but I don't want to run it. I can't run it. That is not the right computer. There we go. Cool, I got the blue box, huh? I'll let you all figure out how to do that on your own someday. All right, this takes us to the actual worksheet. So we run it, nothing to see there. Actually, let me see if I can restart everything. So this square bracket should return a 1. Yay. Okay, so we're starting from fresh. So we made our plotting package, nothing to see here. We'll make our two lists and we'll make a bear. And when we do that, I would like to say ta-da, but that was the picture that was already there, but it just redrew it. So all we supplied for the dashed line was that corner and that corner. So our make a bear package isn't going to be super useful for some other stuff that we're going to do. But you notice when we supplied the information in the dashed line, we supplied those 4 points. How did I get those 4 points? If you have a foul mind, you're thinking you pulled them out of your datum. In a way I did, yes, but I have a very systematic way of reaching into a datum and pulling stuff out. So let's see how to get the line. So first we'll create a function called myLine. It's almost a comedy routine in that somewhere. And it takes a slope, an intercept, one value of x and an associated value of y, and it'll return a tuple, which gives us the left end and the right end from y equals slope times value plus intercept. So point slope form of a line. So we run that, nothing to see there because it didn't do anything yet. And now let's just provide a interesting value of slope. Somebody pick a number between 0 and 1 positive, please. 0.5 it is. And what's a good value for intercept? Let's be stupid, we'll intercept at 0. And we're going to let the myLine function provide the 4 points, x1, y1, x2, y2, to plot the dashed line. The blue dots won't move. Let's see what happens now. Ooh, I was doing that decimal point twice for sure. Okay, so now here we have a case. Is the model worth a damn? Okay, y'all saying no. I agree with you. Why not? Yeah, they're not even close. I mean, it's a miracle that they're on the same plot. So what happens if we make the intercept a bigger number? Let's try 15. I have the close values sitting here as comments so that I don't get completely lost. So we jack with the intercept, and we can hardly argue that that's any better. So as the way it's plotting now, the slope doesn't look terrible because we can't see anything in the blue markers. We definitely need to get the red line closer to the blue markers. So let's just make the intercept negative. That's not doing us any good. So this is just terrible. But given enough time, you would likely start to get close. See how that one works. Okay, so you could narrow it in by trial and error. Yeah, that's clearly a pain in the choose your favorite body part. So it would be nice to have a more systematic way to doing that. Well, we actually already do have one. We just aren't thinking too hard. We know that we can get a correlation coefficient, and that has something to do with slope. And we know that we can get a intercept based on the correlation coefficient multiplied by the mean value of our predictor variable, and we subtract that from the mean value of our observations. And that will give us a line. Turns out that actually will be the best fit line. Let's print our current values of the two numbers. So I've changed numbers from the previous part of the example. Now let's just go ahead and run those normal equations. That's these guys up here. We'll just go ahead and evaluate them, because at this point we're pretty good Python programmers, or at the very least pretty good cut and pasters, and we can cut and paste those in. And so we're going to have a sum of the x, sum of x squared, sum y squared, and then sum of the cross terms. And then we'll divide everything by the appropriate count and use that to get our slope and our intercept. So let's go ahead and run that. And we want to use a slope of 0.129 and intercept of 22.813, not 812, not 814, but 813. I'm sure the last digit has minimal impact. And now when we plot the thing, there's our dashed line, our blue dots. Is that a pretty good model? Yeah, that's a pretty good model. That's a whole lot easier than guessing and plotting and guessing and plotting. There's nothing wrong with guessing and plotting. That is as good a way to get a model as any other, but it's really time consuming. And if you're a bad guesser, it could take what would seem like an eternity to get it. And so perhaps a better way is if a linear model is going to do the job, just go ahead and do the normal equations once and take that guess. Now we have some nice features from that normal equation. We know that it's a minimum energy solution. It minimizes the sum of squared residuals. So that's a good thing. If we know we've minimized the sum of squared residuals, we also know something about the residuals themselves. They tend to be normally or abnormally distributed. They tend to be normally distributed, the residuals. Not always, but if they are, that gives us the ability to make hypothesis tests, interval estimates on the dashed line relative to the blue dots. So where do the normal equations come from? Two ways to answer that question. One is to say we just looked it up in a book and copied it, it was good, and we moved on. Nothing wrong with that, unless you have to defend to a mathematician or in some other class, or maybe even to a client, how you know it's the bestest model in the history of the world. So let's use that calculus stuff, because we make you take 4 semesters of that. Might as well get some value out of it, right? So our linear model, y equals beta 0 plus beta 1x, is the model. And when we do it with our observations, those distances, residuals, can be represented by that epsilon symbol up there. Think of it as an error. Not error in the judgmental form that you're wrong, but error as in you're not at the actual solution. If we square each of those errors, we get the sum of the errors squared is equal to the sum of the quantity y sub I minus beta 0 minus beta 1x squared. And our goal is to make that function as small as possible by selecting values of beta 0 and beta 1. So who remembers from calculus what the necessary condition is for a minimum? For a function to have a minimum? Its first derivative has to vanish. And for a minimum, what do you know about the second derivative? Although we're not going to leverage that at all. Positive definite. If it's negative definite, then it's a maximum, not a minimum. So the necessary and sufficient conditions for a minimum is that the first partial derivatives of the error function vanish. That's a fancy word for, say, equals 0. And we can leverage that requirement by doing the following, well, both calculus and that algebra stuff. So we take the first derivative of the sum of errors squareds with respect to beta 0. And I won't read all the manipulations. When we get to the end of every simplification we can do, we get minus 2 times the quantity sum of y minus n beta 0 minus beta 1 sum of the x's. And we actually can divide out that minus 2 because it doesn't play much of a role. And doing the same for the beta 1 variable, its first partial derivative when set to 0 produces minus 2 times the sum xi yi minus n beta 0 sum xi minus beta 1 sum of xi squared. If we solve those two equations for beta 0 and beta 1, ta-da, we get what are called the normal equations. So the normal equations are not a super revelation. There's nothing magic about them. Somebody a long time ago started with this statement here, that the sum of the errored squares, I want to minimize that by changing beta 0 and beta 1, set the two derivatives equal to 0, solve the resulting linear equation for beta 1 and beta 0 in terms of the sums of the x's, sums of the y's, sums of the cross products, sums of the x quantity squared, sums of the x individuals squared, and produced these solutions. Now there's a more flexible way, which is to use our friend linear algebra instead of calculus. And so in the linear algebra form, I'm now taking great liberties with linear algebra. We start with our same linear model. Y equals beta 0 plus beta 1x plus epsilon. And we'll replace it with vectors. So these now represent each of the observations. So the cap y vector is this column vector of y's. The beta vector is the vector of unknown beta 0, beta 1. The cap x matrix has a column of 1s, a column of the x's, and here I'm showing a secondary column of x squareds. But in your mind, ignore that third column because it's not there yet. And lastly, we have an error term. We can now express the model in vector matrix form. Y is equal to x beta plus epsilon. And if we perform the same calculus on these vectors that we did on the summations, we'll find that what minimizes epsilon transpose epsilon, which is this thing is same as the sum of the errors squared, is x transpose y equals x transpose x times beta. And if we solve for beta, we have x transpose x quantity inverse times x transpose y. So the cap x matrix, the design matrix, is known because we have observations. And the cap y matrix is known because we have presumably paired observations. Transposing a matrix is easy enough to do. We just interchange the rows and the columns. Or if we're doing it in NumPy, there's actually a transpose function, which, lo and behold, interchanges the rows and columns. And even though we wrote the solution here involving an inversion, you wouldn't normally invert the matrix. That would be an act of dumbness. Instead, what you would do is you would solve this linear system here for beta, because then you only have to do it once. If we have a matrix of, say, 10 rows and 10 columns, inverting it is the equivalent of solving 10 linear systems, where we only need to solve that linear system once, not 10 times. And so here's a linear solver in NumPy. Remember what the linear solver was called? I think it was called linsolve or solvelin, one of the two. All this does is Gaussian reduction with partial pivoting. And then we need some homebrew script to handle some multiplication, matrix vector multiplication. Now we're going to build our design matrix. So our first one will just have two columns. It's going to have the column of 1s and the column of x's. So we declare the column length equal to 2. And then we'll get the row length from however long our sample weight inputs are. And we're going to create a matrix full of 1s, a transpose full of 1s, a y vector full of 0s, and then we're actually going to read from our lists directly into the matrix. So this is where the primitive way of doing things is kind of a pain in the neck. So we read from sample rate, we put it into the correct location in the design matrix. We read again from sample weight, correct location into the transpose of the design matrix. We read sample length, put it in the correct location of the y vector. Then we build some space for the X transpose X matrix and the X transpose Y matrix. Then we create them using multiplication, matrix multiplication and matrix vector multiplication. Finally, we create space for our beta 0 and beta 1. And we run our linear solver function, which does this guy up here. And we will recover, the slope will be in beta 1, and the intercept will be beta 0. We'll set our x low and our x high the same as before, and let's see what happens. You can see from the picture we get the same answer. Oh, what did I do wrong there? That was good. We got the red box of encouragement. You know, Grace, come on. Yeah, the linear solver's not yet defined. There we go. Okay, ta-da. So we did it all by ourselves, no help. And that in and of itself was kind of cool. There was, if we look in here, there were no special packages that were used, with the exception of Make-A-Bear, which uses Matplot library. So everything else was done pretty much in, I'm looking to see if there's any package installs there are not. It's all done in primitive Python. We could have done that without the internet working, not being able to download stuff. So you saw it here first, how to do stuff without the internet working. Well, what's the value of all that? In one sense, probably none, but in another sense, the value comes when we have more than one explanatory variable. So let's say our model y is equal to beta 0 plus beta 1x plus beta 2 something else. If we start taking derivatives, now we have 3 equations and 3 unknowns that we have to solve for the unknown betas. And it's not too hard to fathom a case where that's going to start to be really difficult to do mathematically. But operationally, using our friend the computer, we simply add a column to the design matrix, reconstruct the X matrix, X transpose matrix, X transpose X, X transpose Y, solve the system, boom, we're done. So here we're going to just make 2 different lists. So 0, 1, and 3, and then minus 2, minus 1, 0, 1, 2. So the blue dots show us our list, and we have no idea what the correct slope intercept is, so I guess the slope of a half. Intercept of 1 will plot from minus 3 to 3. We run the thing, and there's our dashed line. Your opinion, is that dashed line an adequate model of the blue dots? The word it chose was adequate, so yeah, it's adequate. Do you think we could come up with a better one without working very hard if we were just doing this on pen and paper? That'd be, yeah, absolutely. Of course you could. You could draw a straight line that balances way better. Let's go ahead and first we'll get the linear model that fits those observations best. So there's no change here from the prior code. It does everything the same as before. The only difference is the data have been changed. So just run that guy. And yeah, so there's our best model. It's both coincidental and it was by the choice of the data that I used that the line actually passes to the point 0, 1, which happens to be a data point. That is rarely the case with real data. So that's a good straight line, but do you see any evidence of curvature in these data? Yes, you do. Let's add a couple more columns. Let's add an x squared column and an x cubed column. So what we're doing in that case is in our design matrix, we're just adding additional columns. And I've chosen to make the next column the x squareds, the next one x cubes, but it could be other letters of the alphabet if you wanted to. So So let me get back to it. So now we have a total of 4 columns. A column of 1s, a column of x's, a column of x squareds, and a column of x cubes. So now we'll go ahead and the only changes there are building the different parts of the design matrix and its transpose. So we have a couple more lines of script here. Most of the rest is essentially the same. This is the same. No change here. No change here. And finally, we solve the system for beta. And now we want to go ahead and plot it. Since I like nice smooth plots, that's the last one I'm going to do in this presentation. We will plot from -2 to 2, 20 things, and use that to draw a plot. And then we're going to plot the data and then plot our model that we just fitted and see what we get. We do that, and there's our model. Hardly perfect, but that was fairly minimal work to draw a cubic through the blue dots. And so concluding on this part, in core Python, there's a reasonable amount of work to write a script. You got to get your linear solver script working reliably. So be thankful we don't make you do that, because this is not the 1970s anymore. But let's look at some easier ways to do the same thing. So we're going to stick with the same data. But now we're going to use a package called stats model. So first we need NumPy, we'll need pandas, we might need statistics, so we'll just import it. And then for matplot library, we're going to use pyplot, and we'll import it as named plt. And we're going to take our data, xxx and yyy, and create a data frame. And we look at the data frame, and indeed the data frame looks like how we expect it. It is somewhere up here. It's based on those. Okay, so we have our data frame. Relocating. So first we're going to use a program called stats model, and it uses a interesting syntax. So import statsmodel.formula.api. API means applications programming interface, and basically it gives us its own little separate programming environment that it can manage. And we're going to import it and name it Smurf, SMF. So now we will initialize and fit the linear regression model using stats model. So we just create an object named model because I have no naming creativity. We run the Smurf ordinary least squares, which is making the springs short, and we tell it in the data frame, find the key named y, and we're saying that it is linearly associated with a key named capx. And the data that we're going to use is inconveniently named data, so that is admittedly a very clunky syntax. And then we are going to instruct it to, when it does this, it does all the work at once. And from the output of model, we're going to create a model fit. And so we're giving it the fit method, and we'll put the result into model, and then we'll have our linear model done. And notice it took a little longer than our home built code because it's going out to the internet and seeing if it can check the answers first. Now we're going to go ahead and extract the parameters, and that's just there for show. Those parameters are going to be the same as the ones we got doing it by our homebrew way. We're now going to predict the values, and we're going to put it into a variable named ypred, and then we'll plot the two. And there we go. We get the same result as doing it by hand. Or not by hand, as doing it by our own code, but considerably less. If you ignore the plotting part, remember that could be its own function, completely hidden from you. You have one You don't even need the parameters back. 2, 3, 4 lines of script instead of, we must have had way more than 40 before. So at least a 10-fold savings in lines of script. And it still works, so that's kind of cool. You'll notice that there's a semicolon at the end of the plot call. What that does is that suppresses some of the annoying output that you don't want. Now let's go ahead and add a column. We'll add the x squared column. And we can go ahead and do the x cubed if we want. In this case, because it's a data frame, adding a column is real simple. We just name the data frame, put out the square brackets, create a name for our new column. Hopefully it doesn't match the names that are already there, or we'll break stuff. And then into that new column, we'll take the data frame again. We'll use the cap x value, which is already there. We'll square it. We'll stuff it into our new name. Then we will modify the call to the fit function. We're going to say that y is now proportional to x plus xx. So it's like two different input variables. They happen to be named x and xx in this case. So we got Dos Equis and uno. It doesn't come out of my mouth right. So this is just the beer fit. This is basically the Michelob Budweiser equation. And we'll go ahead and run that. And now when we do the plot, and we've picked up the curvature, and that is one way of doing linear regression and multiple linear regression. And it has the nice feature, it's relatively trivial to add predictor variables in this case. There's another package called sklearn, and in sklearn there's a linear model method, and from that we're going to import linear regression. And this one kind of works in a similar fashion, although we have to build two objects. One object is the predictor object. The second object is the predicted, or the response. And so here we're going to create an object named predictors, and it's just going to have the two keys associated with our data frame that we've already built. And then we're going to take from the data frame predictors, and we're going to assign that to something named capx. And from the y, we're going to assign that to lowercase y. I think the cap and lowercase are just my brain working in a funny way when I wrote this. And we're going to run the linear regression function, and we're going to put it into an object named lm. And then from lm, we'll fit it. X is the design matrix, Y is what's being predicted, and it goes into model. And from that we can get the intercepts, and they use the term coefficient to represent beta 1, 2, 3, and so on. And beta 0, they call it the intercept, and here it's shown as the alpha. So let's run that fit. And now when we run the model, we get the same result. So two different ways using packages. By all means, for your stuff, don't do it in primitive Python, because that's going to be prone to a lot more errors. The worst error you'll get using a package is the pink rectangle of encouragement with uninterpretable error messages. The worst that can happen when you write your own code is it appears to run and it kind of sort of works, and you can easily delude yourself into thinking you did it right when in fact you didn't. Let's go back to the original Texas Instrument manual example. So we'll put sample length and sample weight in, and we'll convert them to a data frame named data. Anyone speculate a guess why I choose the name data for the data frame? Well, you'll see in a second. So there's our data frame. We chose the name named data frame because that cell and the next cell were completely obtained by using the miracle of what do you do with a knife? No, not stab and run. Cut and paste. So we cut and paste from previous stuff. So at that point, we want to minimize any typing. I did relabel the labels in the plot call. So now let's make sure I got these all set up. Yeah, those are loaded. And there is our Texas Instrument data fitted using the, I think that was the sklearn package. And we could do that with other linear packages. Okay, so I'm about to let you all go so we can go have lab in 2 minutes or less. Quick review of the day. What was the name of today's lesson? Regression. Yeah, not progression, but regression. We're going backwards. We'll do the progressive class at some point in the future. Our main goal was fitting blue lines through red dots. We chose a measurement of how good the blue line went through the red dot called residuals. Actually, the sum of squared residuals. We can recover the model parameters, the beta 0, beta 1, beta 2, and so on and so forth, using a set of equations called the normal equations. We also looked at how to do it using ordinary linear algebra. We found out that the normal equations are not some magic thing. They're simply a consequence of setting the first partial derivative of the error function, the sum of squared residuals, for each of the unknown betas to 0 and solving for the unknown betas. That's all that's going on in regression. Then we looked at a few ways to do it and draw cool plots. Okay, so let's see if Blackboard came to life. I'm guessing it didn't. Ooh, way worse than didn't. I'll just say it before I end the recording. So on Blackboard, on the home page for this class, there's the link to the syllabus, and below it there's the link to the design project team, the semester project teams. There's only one team that has admitted to being a team. So the rest of you all need to get me that information so I can complete the table. I'd like it by tomorrow. The team that already sent it in, you all don't have to do squat. You're good. Just get together sometime and start figuring out which projects you're going to work on. I suggest you do, actually either one of them is good. You actually now have all the content you would need to do either of them. You might have to do some research to make it look like you did some work, but all the tools are there now. Yep, by tomorrow, please. Turn in your teams, and for the invisible people, you should make a team of the two invisible people sitting on either side of you. For the visible people, this would be a good time to get out in the hallway and decide that you're going to be a 3 or 4 person team and get